continue. So this is exactly what we have done in the forenoon session. We performed the canonical transformation generated by a given type of the generative function f1, and the result was something interesting. We transformed from some qp to capital K, capital P, a new set of canonical variables, and the transformation resulted in a new momentum P, which was equal to E by omega, where E is the total energy of the harmonic oscillator and omega was the angular frequency of oscillation. And since total energy is a constant in the case of a harmonic oscillator, we obtained P is equal to a constant. And further, we obtained the new momenta Q to be equal to something like omega t plus some alpha, where alpha is a constant of integration, which can be set equal to 0 if needed, depending on the initial conditions. So, moreover, we have seen that the transformed Hamiltonian of the problem K was obtained as simply omega into P. Means K was cyclic in the newly introduced coordinate capital Q, from which we concluded that the new momentum must be a constant, and physically also we argued that the new momentum will be a constant as far as energy and omega are both constants. In essence, or in short, what we have achieved by this canonical transformation is that we have changed, or we could effectively change the problem of harmonic oscillator in such a way that the new momenta is a constant of motion and the new coordinate capital Q is increasing linearly with the time. So we could change the oscillatory motion. Okay, so that is a conclusion. The canonical transformation has resulted or has helped us to transform. I can use to change or to transform. Actually, it is a transformation. Transform the oscillatory motion. The oscillatory motion of a harmonic oscillator into an equivalent and mathematically simpler translational motion or linear translational motion. So that is our final outcome of such a canonical transformation. So this was, I already mentioned that every transformation is meant to mathematically simplify the procedure. So this is exactly what has happened. Okay, the oscillatory motion, which is the characteristic motion of a harmonic oscillator, has been now converted into an equivalent translational motion without losing the real physics, or without losing what is actually happening in the system. No details are lost, but mathematically we are able to make such a conversion. Okay, and if you can see that we had an equation that we had also Q is equal to, we had an equation for Q. I think some equation was there which is equal to some 2p by m omega. You can refer back to your notes. In times sine Q, we had a relation like this. I think some equation number 4 or 5 which we had written. So Q is equal to So this is the equation that I am talking about. So you can just see this equation. Equation number 4, please. Equation number 4 at the bottom. Q is equal to root of 2p by omega into sine Q. So you have that equation. I'm rewriting that equation. So that was equation number 4. Equation number 4 is there. Now let me do one thing. Let's substitute capital P. Okay, since capital P is equal to, what will be capital P? Capital P will be equal to E by omega by this token. Okay, P is equal to E by omega. What will be Q becoming? Q is equal to, just let's see that when you substitute that P equal to E by omega, so what will happen is that this Q will become root of 2E divided by omega is already there, one more omega comes, so it will become 2E by m omega square times sine Q. Let me call this one, which can be, again, if you want, you can again modify that. What is Q here? Okay, so let me do like that. So let me just make modification. Sine Q, and what is Q? Q is equal to, from this relationship, Q is equal to omega t plus alpha, right? So I can substitute for Q also here, that is omega t plus some alpha. So let me call some number for this one. Now when you look at this particular equation, you will see that this is the usual solution of the displacement for a harmonic oscillator. This is of the form which is of the form Q equal to some amplitude term Q0 times some sine omega t plus, you say, some constant alpha. And once you set alpha equal to 0 by initial condition, you know alpha is usually known as the initial phase. Alpha in harmonic oscillator terminology is known as initial phase of the particle. Okay, initial phase or phase constant. Usually we have been denoting it as phi 0. Okay, or EPO, whatever it is. Okay, so which you can set alpha can be set equal to 0 for convenience, for suitability. And this Q0 is nothing but the amplitude, right? Okay, so Q is the displacement. Okay, Q is the displacement of SHM. Maybe, okay, no, we have been writing it as some in terms of x. X is equal to some A sine. This is the usual way in which we write, plus or minus phi 0, and like, or y is equal to A cos, whatever it is, or any linear combination will also do. That's the thing. So instead of x, I have used Q because we have been referring to generalized coordinates as QJs. That is the reason why x has become Q over here. So Q is the coordinate or the displacement of the harmonic oscillator. And now, so what is Q0? You can see that from our comparison. So this term is actually the Q0 here. Is not, this is the Q0. So where Q0 denotes the amplitude. So it's in place of this A. So A is Q0. And you can see that this is exactly the amplitude that you are already familiar. Already amplitude term. Okay, how come you understand that? Because you remember what is the do you remember what is the expression for the total energy of harmonic oscillator? What is the expression for the total energy of the harmonic oscillator? Can anybody help me to tell what is the energy or what is the expression for the total energy of the harmonic oscillator? When you sum up kinetic energy and the potential energy, okay, you will get the total energy. And you remember in our previous graph, yes, here. My question is that what is the total energy over here? So maybe you remember, I think I recall that the total energy we had proved that is equal to half m omega square a square in your lower classes. Okay, the total energy of the harmonic oscillator is equal to half m omega square a square, where a is the amplitude. Okay, so which is a constant, because amplitude is a constant in undamped motion. So here E is equal to half m omega square. This is a very standard and established result. Okay, half m omega square a square. That is the thing. Now in place of A here we have Q0. A ke pagaram namukku Q0 aanu. So I can write this is equal to half m omega square Q0 square nu ezhudam. Idil ninnu Q0 endaanu kittille. So what you will be getting Q0. So from that you will be getting Q0 is equal to, you just cross multiply it. So 2 into E. So that is 2E divided by m omega square with a root. Is it clear? And can you see that this is the same thing that has appeared in equation number X here. So that's the same term that has appeared over here. why I just invoked this idea, because so that you have to understand that our canonical transformation which was done with the help of the f1 that we have taken. So hope you remember what is f1 is equal to. F1 we took f1 is equal to half m omega some q square cot q. ഇതാണ് നമ്മൾ f1 ആയിട്ട് പ്രോബ്ലത്തിന്റെ തുടക്കത്തിൽ എടുത്തത്. So this f1 or this generating function which is of the form f1 has helped us to transform the problem from the oscillatory one into a translational one without losing any physics that was involved in the problem. നമ്മുടെ പ്രോബ്ലത്തിൽ അടങ്ങിയിരുന്ന ഫിസിക്കൽ പ്രോപ്പർട്ടീസ് ഒന്നിലും തന്നെ യാതൊരുവിധ നഷ്ടവും കൂടാതെ തന്നെ ഈ ട്രാൻസ്ഫോർമേഷൻ ചെയ്യാൻ പറ്റിയിട്ടുണ്ട് എന്നുള്ള കാര്യമാണ് ഞാൻ ഇക്വേഷൻ എക്സിന്റെ ഡിസ്കഷനിലൂടെ നിങ്ങളോട് പറയാൻ ഉദ്ദേശിച്ചത്. ഹോപ്പ് യു അണ്ടർസ്റ്റുഡ് ഇറ്റ്. ഓക്കെ, now this is exactly what we have achieved. We could convert an oscillatory motion into an equivalent mathematically simpler translational motion by doing such a canonical transformation, at least in a familiar system like harmonic oscillator. Ini ഇതിന്റെ ഒരു pictorial representation, I told you that the physics is not lost. So this is exactly what you have to remember, that okay, the physics of the problem means the physical reality of the problem is preserved. നമ്മൾ ട്രാൻസ്ഫോർമേഷൻ ചെയ്ത് കഴിയുമ്പോൾ പ്രോബ്ലം തന്നെ മാറിപ്പോകരുത്. whatever information you had in the problem in the initial coordinates small q and small p will be there in the new coordinates capital Q and capital P. Okay, that's what we are verifying time and again. Now in order to further justify my statement that the physics of the problem has been preserved or it is maintained, let me go to some graphical representations. Okay, നമ്മൾ പറഞ്ഞ കാര്യത്തിൽ കുറച്ച് graphical representationലേക്ക് ഞാൻ പോകാൻ പോവാണ്. So see that where I have already made some graphical representations, you can just see here. So for the time being, what I have done, okay, I have drawn here some graphs. What are these graphs? Let's see that. So the left side set of graphs are the graphs in the original coordinates small q and small p, and the graphs given on the right side are related to the new or transformed coordinates capital Q and capital P. So let's see what are the things that we have drawn. I am writing the relevant equations on the LHS and RHS of these two graphs. In the original coordinates or old coordinates, this is old set of coordinates, and this is the new or transformed set of coordinates. So you know that in the old set of coordinates, the coordinate q or the displacement q is given by q equal to some q0 into sine omega t. Okay, as we have just established right now, I am setting alpha equal to 0. So let me set for the time being alpha equal to 0, which is an initial condition. It's a constant of integration which you can make arbitrarily equal to 0 for a trivial simple case, right? So q equal to q0 sine omega t. So what will be the nature of the graph here? Of course, the graph will be sinusoidal graph, right? Okay, so if I am trying to draw the graph over here, you can see that the graph should be something like this. See the graph, this is exactly what we have been drawing or we have been doing, is not in a harmonic oscillator. So this is what is going to happen, and it goes on with the time. So you know, so it's a qt graph. Okay, or you can take omega t also here, no problem. Okay, so what is here? Of course, this amplitude term, this is q0, and of course this thing is minus q0. So that is your usual graph. Clear? Now the second graph downwards is at the bottom is nothing but the variation of momenta. Okay, or the momentum of the harmonic oscillator with the time in the original qp space. So you know, the momentum we have proved that P can be written as some P0 into some cos omega t, because it will be mq0 dot or mq dot, which is sine become cos. So it is some P0 cos omega t, right? So the graph is going to be, what will be the graph? Okay, of course the graph is going to be a cosine graph, right? With its amplitude as P0, right? So the cosine graph means it should start somewhere over here, and then maybe it is coming down, then it goes on down, then it goes up. Okay, just going up and down. Of course there will be a phase difference of pi by 2. between the top graph and the bottom graph. It may not be clear when I have drawn it. Please neglect it. Anyway, you can understand when you compare the initial thing. So this is actually P0, the P0, and this will be of course minus P0 when cos omega t goes negative. So these are things. And what I have drawn at the bottom, of course, you know, this is nothing but the phase space diagram. So this is the original phase space diagram in the original coordinates, phase space diagram. Okay, the phase space trajectory of the system, harmonic oscillator. Already we have established and discussed many a times. So maybe you can just put up an arrow which is in the clockwise direction. So that is the thing. Now, on the right side, let's see in the transformed coordinate system, what are these graphs becoming? You can see that left side is denoting exactly sinusoidal variations of q and p, the coordinate and momenta. Okay, but on the right side, you can see what was our q, capital Q. I hope that we have established that our q, the transformed momenta, it was proved to be equal to some omega t plus some alpha, and I have set alpha equal to 0, so it is simply q equal to omega t. Q is equal to omega t. So I have taken q on the y-axis and t on the x-axis. So how should it look like? Of course, you know that the graph must be a straight line. If you set alpha equal to 0, of course, then the graph will be going from here. Or if you don't set alpha equal to 0, of course, the graph will be something like this. Is it not? This is going to be the graph. And if you set alpha equal to 0, the graph will be getting shifted. You know what is going to happen. So what will be, this one will be alpha here, right? So this is going to be alpha over here. The y coordinate is alpha here. Okay, this is the alpha here. And if you set alpha equal to 0, only what is going to happen is that this particular graph will be getting shifted. Okay, you know, it will be getting shifted to the origin. This is exactly what is going to happen. So this will be the case when alpha equal to 0, but let me keep it without alpha equal to 0. So this is optional, of course. Alpha can be set equal to 0 in the trivial case, more simple case. I think you follow me, right? Now, what about the capital P? So, you know, the capital P, we have seen that P is equal to E by omega. That is what we have seen. P equal to E by omega. And we have seen that E is a constant, omega is also a constant. So, there is no time variation for P. Since the newly transformed Hamiltonian is cyclic in capital Q, it renders the new momenta, capital P, as a constant. So, this is a constant. That's a constant. So, how would the graph look like? Of course, you know, the graph is going to be again a straight line. That is what parallel to the time axis. So, this will be the graph where you can see that this value, where this particular value is. So, it will be a constant at E by omega. So, this value will be equal to E by omega. So, that is what we have seen. And now just you look at the graphs on the left side of the arrow and the right side of the arrow. You can see the transformation has finally resulted in converting the problem which was completely oscillatory in nature into completely linear in nature. That's why I concluded in the previous slide that the effect of this canonical transformation generated by F1 in this particular case is to convert an oscillatory motion into a translatory one, which is mathematically easier to analyze. And you know, even the graph shows that the problem has become much simplified than the left side one. Hope you follow me. Believe it or not, you can see the physics of the problem is not lost in this transformation. And how can we prove that? We can prove it by considering the phase space trajectory. See, what will be the phase space trajectory in the case of the transformed coordinates? So in the case of the transformed coordinates, you will see that the phase space trajectory, since you know P is a constant, it will not change with Q. So the phase space trajectory is going to be once again like a straight line. In the transformed coordinate, the phase space trajectory is going to be a straight line. Okay, why? Because P is equal to a constant. P is equal to a constant. It is independent of Q. So if I draw the variation of P with Q, it must be a graph which is what parallel to the Q axis. Okay. So this is the transformed phase space trajectory. And how can you ascertain that the physics of the problem is not lost? Let's see how to do that. If you want, you can just we can take the discussion to any level, but okay, we'll limit it like so. This is the QP phase space. Can you just find out the area of the phase space trajectory or area enclosed by the phase space trajectory. So means I'm talking about this particular area. What is the area enclosed by the phase space trajectory? Because it can also give some information on the nature of the problem. So for example, the area here, the area A is equal to, area of the ellipse, no, right? What is the equation for area of the ellipse? We have discussed in our Kepler planetary laws that the area of the ellipse is equal to pi AB, where A is the semi-major axis and B is the semi-minor axis. Okay, so you need to know what is the semi-major axis. So this point is nothing but the semi-major axis. What is that? This is nothing but the amplitude. It's not the amplitude term. And right now we have seen that the amplitude is Q0, right? So this amplitude, that's a maximum value of Q. That's Q0. And what is this Q0 equal to? We just have proved in the previous discussion that this amplitude is equal to root of 2e divided by m omega square, right? So this one should be equal to root of 2e divided by m omega square. And what is this one? This is nothing but you can see that that is the see the maximum value of p, and you will see that that is equal to root of some 2me, that is equal to root of some 2me. Okay, so I can say this value is equal to, we are already had discussed, I think, that this is some root of 2me. Okay, so where the that this denotes the mean position, this denotes the mean position where the energy is purely kinetic. So automatically total energy will be equal to purely kinetic, so it will be p square by 2m, right? Because the potential energy term will be equal to 0, so p equal to root of 2me, right? So this will be the thing. So this is the semi-minor axis B, and this is the semi-major axis A for the harmonic oscillator. So once you just multiply these two values, let's see what you're going to get. So pi into A is equal to root of 2e by, I should put up by m omega square times B. What is B? B is equal to root of 2me, and you make the cancellations. What you will see is that this is nothing but so 2 root 2, it's 2, then pi is there, that m and root m will be getting cancelled, okay, and that omega also will be coming out. So what you are finally left out, that area is equal to some 2 pi e, right? 2 pi e divided, because e is square, e divided by omega. So this is the area of the phase space trajectory in the old coordinate, and you will see that this area will be maintained, or the area will be preserved even in the transformation. In the transformed coordinate, this area will be preserved. How do you argue that? Okay, so let's do one thing. So right side you can see the transformed phase, what you can say, phase space. So this is the transformed phase space. Transformed phase space. In the transformed phase space, I have to find out the area. So, but there is a question. On the LHS, the area is a closed one, right? But on the RHS, you feel that the area is just going on. But we should put up a limit here. How do you put up the limit? Because the motion is actually a periodic one, right? The motion is a periodic one. So as we have discussed earlier, pointed out earlier, the phase space trajectories for a periodic motion, okay, like an oscillatory motion of the harmonic oscillator, will be always a closed trajectory. That's why we got a closed trajectory, phase space trajectory here. But on the RHS, since we are converted it into a linear or a translational motion, the phase space trajectory is not going to be closed. But you have to make a comparison. How do you make the comparison? Let me suggest a method. You know that okay, the entire trajectory, right? Okay, on the left side, you start from one point. Okay, you go to the other point. You complete one trajectory. You know that it's this complete trajectory denotes the time duration. The time t is equal to capital T, right? So the trajectory you have drawn here is over an entire cycle, means over an entire period of time equal to small t equal to capital T, where capital T is a period of the SHM, right? So ഈ ഒരേ ടൈമിന്റെ ഉള്ളിൽ ക്യാപിറ്റൽ ടി എന്ന് പറയുന്ന ഒരു പീരീഡിന്റെ ഉള്ളിലാണ് ഇങ്ങനെ ഒരു നമുക്ക് എന്താണ് ഒരു elliptical trajectory കിട്ടിയിരിക്കുന്നത്. In the next cycle, the trajectory will be getting repeated over and over and over again. ഓക്കെ, അപ്പൊ നമുക്ക് ഇതിനെ രണ്ട് ഏരിയ ഒന്ന് കമ്പയർ ചെയ്യണമെങ്കിൽ ഇതേ ക്യാപിറ്റൽ ടി എന്ന് പറയുന്ന സമയത്തിന്റെ ഉള്ളിൽ കവർ ചെയ്ത ഒരു ഏരിയ ആണ് ഇവിടെ കണ്ടുപിടിക്കേണ്ടത്. Then only you can make a comparison. How do we do that? Okay, so let me do that. So what is our equation? This is our equation for capital Q, right? So we have capital Q is equal to omega t. I'm setting alpha equal to 0 for the time being. Okay, so Q is equal to omega t. When Q equal to omega t, you know that this omega, okay, but this omega is nothing but 2 pi by capital T, right? Because omega is equal to 2 pi EF, a linear frequency, and F equal to 1 by capital T. So into small t it will become. Is it clear? So let me put up my condition here. What is the condition that we have drawn on the LHS? The trajectory was drawn for a time equal to capital T. So let me find out the value of Q when t is equal to capital T, so that we can make a comparison. There should be a justice, no, on the LHS and RHS, because we are going to compare the area that has been completed, the area that has been inscribed during the complete cycle. So when t equal to capital T, what will be the capital Q equal to? The capital Q value will be equal to, so of course it will be equal to 2 pi by capital T, 2 pi by capital T into capital T. So you know that that's going to be cancelled, and so you'll be getting, when small t equal to capital T, the value of capital Q will be equal to 2 pi. So what I'm doing, let me say that somewhere here, when the time is 1, you'll be getting 2 pi. So the value of Q will be equal to 2 pi at some point of time. Okay, so let this be the thing. So let me mark it. Now let me find out what's the area that has been covered by the phase space within the same comparable time of one time period. Okay, and of course one thing I just left out. What is this P equal to? Of course this P is remaining always equal to E by omega. So this is E by omega. Now see, this is a rectangular phase space region, and tell me what is the area of this rectangle. You will see that the area is equal to, once again it is length into breadth, so that is E by omega into the length is 2 pi, so into 2 pi. And not a surprise, it should not be a surprise if you believe in the technique of canonical transformation, you are getting the area as 2 pi E by omega, and here also you can see that the area is what? Preserved, 2 pi E by omega. Okay, fine. I hope that you understood, or at least this is enough and more to believe that canonical transformations leaves the physics of the problem unchanged. Therefore, that is our conclusion for the topic or of the discussion. Therefore, the canonical transformation leaves the physics or the dynamics physics of the problem invariant. Physics of the problem is remaining invariant. So, but at the same time, on the other side, it has simplified the problem much. Okay, that's just a simple demonstration. I just discussed it out of our intellectual satisfaction to tell you that things are remaining the same. You may skip it if the discussion is too lengthy, and focus on whatever is in your textbooks for the time being. Okay, fine. Any questions on what I have discussed so far?